Hi friends, in today's video I'm gonna talk about nucleophilic substitution reaction or SN2 reaction. The reason why it's called nucleophilic substitution is that we have a nucleophilic attack in the mechanism, and the reason why it's called SN2 is that we have two reactants participating in the rate determining step, which is the only step we have for this reaction. So let's start talking about the conditions. For an SN2 reaction to happen, we have to have a very good leaving group. Here is the list of good leaving groups. So here we have a chlorine, which comes the first place, then bromine, then iodine, then H2O+. The weaker is the base, the better is the leaving group, and the stronger is the acid, the conjugate acid. Here is the list of poor leaving groups. The stronger is the base, the weaker is the conjugate acid, and the worse is the leaving group. For the substrate, it's the carbon-like bonding to the leaving group. It has to be primary. In some cases, we have secondary carbon, but the reaction of SN2 with a secondary carbon is slower than SN2 occurring on a primary carbon. And then we have a nucleophile, which has to be strong. Here is the list of strong nucleophiles. So we have iodide, bromide, chloride. You have just to remember that the weak nucleophiles are usually water and alcohols, and all of the rest are pretty strong. And for the solvent, it has to be polar and aprotic for this kind of the reactions. Usually we are just looking into the leaving group, then the substrate, then the nucleophile, and the solvent comes at the last place. Now let's talk about the mechanism. So for SN2 reaction, the first step is the leaving group which leaves. We have here a bromine atom that leaves. This is the first step, and this reaction happens at the same time. Like we have one main step for the whole reaction. We have at the same time the bromine atom, which is the leaving group, which leaves, and then from the other side comes the acetate ion, which is the nucleophile, will attack the carbon. We can't have 5 bonds, 1, 2, 3, 5. First, the bromine atom leaves, and then after a few seconds, the acetate ions comes to bond to the carbon atom. And then this is the transition state for this reaction, but it all occurs on one step, one main step. As a result, we have a bromide and this CH3, this methyl group attached to the acetate ion. This is the result of this reaction. Now let's talk about the order of the reaction or the rate of the reaction. An SN2 reaction is called SN2 because it's a second order reaction. We have two reactants participating in the main step, which is the rate determining step for this reaction. We have the CH3Br and we have the acetate ion. So this is the rate order of the reaction. It's a second order reaction. Now let's talk about the stereochemistry of SN2 reaction. We have here a chiral carbon with 4 different bonds. So we have to think about stereochemistry. As I told you earlier, SN2 reaction occurs generally with primary carbons, but it can happen with the secondary one. It's just much slower than an SN2 reaction that happens with a primary carbon. So here we have for the stereochemistry, we have the leaving group that leaves. Then at the same time, the nucleophile comes and attacks the carbon. So we have the leaving group from this side. The only way that the SH can attack the carbon is by going this side. It can't go this side since it's going to be blocked by the iodine. The only way is attacking it from this side. So in the beginning we had an S configuration for this molecule, since the priority is for iodine. Then we have the ethyl group, then the methyl, then the hydrogen. It's going this way, so it's an S configuration. But since we have an inversion of configuration, like a backward attack of the nucleophile, will have the reverse, like the SH is going from this side. The priority is for the SH, then for the ethyl, then the methyl, and the H, it's going from this side, making it an R configuration. So whenever you have a chiral carbon as a result of an SN2 reaction, you have to think about stereochemistry. If we have an S configuration, you have to reverse it into an R configuration. And if you have an R configuration, you have to draw the opposite, which is the S configuration. And obviously the SH nucleophile is pushing the other atoms into this side. They are flipping, like the H, CH3, CH2, CH3, to make more room for the nucleophile. Like in the beginning we had them flipping toward this side, and now toward this side.